Software Engineering Radio episode 73, Real-Time Systems with Bruce Powel Douglass. Welcome listeners to a new episode of Software Engineering Radio. This is another episode in our series on embedded software development, and this time we're talking to Bruce Powel Douglass, the chief scientist and, well, whatever that means, he'll explain it in a minute, of Teleological. So, Bruce, welcome to the show.
Well, thank you very much. Happy to be here.
Thanks for agreeing to join the podcast. So why don't we start by having you introduce yourself and your personal background, your professional background a little bit so people know who you are.
All right. Well, let's see. I was raised by wolves in the wilds of Oregon. I taught myself to read when I was 3, taught myself calculus when I was 12, quit school when I was 14 and went to college. Currently, I got 3 degrees, a master's, bachelor's, and a doctorate. My doctorate is in neurocybernetics, which is the study of information processing in biological neural systems.
Okay.
I've been involved in software for a long time now. Ran my own software company, doing statistical and numerical analysis and various kind of lab embedded work. I've been involved in various kinds of safety-critical embedded systems for the last 25 years. Everything from medical systems to fire control systems, aircraft designs, and both for the system side and for the software side. For the last 11 years, I've been working with iLogix and now Teleological as a chief evangelist, doing some product visionary work for the Rhapsody tool, doing some standards work. I'm one of the authors of the contributing to the UML standard, the UPDM, Unified Profile for DODAF and MODAF standard, UML profile for schedulability, performance, and time, as well as a number of other standards. And I also do a lot of consulting in the real-time embedded marketplace all over the world, in Turkey, in Europe, in Asia, in the U.S., in Canada, and so on.
Aren't you an IBM employee now? I heard rumors that Teleological was bought by IBM.
Well, there are rumors to that effect. IBM has issued an offer, but at the present time, the offer is not yet done. There are some conditions as to the number of percentage of proxies they can purchase, and so on. This is expected to be resolved by the end of this month, and then if it goes forward, the sale would probably take place in September of this year.
Okay, but let's not talk about these kinds of things. Let's get to the meat, which is real-time systems. So why don't we start by you explaining a little bit what a real-time system is and what some of the distinguishing properties of these kinds of systems are.
All right. Well, the most important aspect of real-time means that time is essential for correctness. Now, one of the ways that people model time is deadlines, and that's really the most common way. But it really is just a subset of the overall real-time systems development and set of concepts. The core aspect of real-time is just that time is essential for correctness. And within that context, there are things like hard real-time systems, which are usually modeled after deadlines. There are soft real-time systems where you model things as over some stochastic measure of timeliness, such as minimizing mean lateness, for example, doing average throughput, average boundaries, but it's still considered real time. But timeliness is essential to correctness, is the essential characteristic of a real-time system.
And then the level to which timeliness is important, like whether one missed deadline is already a failure or whether that's just, a problem that can be fixed with subsequent, cycles, that depends on the specific kind of system you build. Right.
An action is said to have a deadline. It's a common way to model it. But what that is really a simplification. And again, the simplification is why do people do that? It's because the math is easy, okay? Yeah. There's think of a step function in the case of deadline. It's called the utility function in general. It is the value of the completion of the computation over time. If that value goes from infinity or 1, depending upon how you want to model it, to 0 at some instant in time, that instant in time is called the deadline. But actual fact, in general, there might be a decreasing value, a decreasing utility function, which may not just be a step function.
So you're saying it might be, if it's a little bit late, that's not quite as good, but it's not necessarily a fatal failure.
Right, in which case it's not really a deadline kind of driven system. But people nevertheless use deadlines to model it because the math is easy.
Right, sure. Yeah. And another thing you already mentioned is responsiveness. That goes to the average throughput, I guess. That means, for example, a system can take 1,000 measurements per second, but it doesn't really matter if a specific measurement point in time moves by a microsecond for or back.
That's absolutely true, and maybe even unimportant whether or not you get all the measurements.
Right.
For example, you may be able to have one be late, you may be able to drop it altogether. It depends on the nature of the system. There's a saying that hard real times are hard, but soft real times are harder, right? And again, it's harder just because the math is harder. The math is more complex to determine whether or not you have adequate throughput.
That's actually a good point. I've never looked at this way. I always thought that more or less hard deadlines, hard real time is the real challenge. But
right. Well, chapter 11 of my book, Doing Hard Time, goes into this concept in some detail.
Actually, it's a good point. We should point people to the book and put that into the show notes. Book is also basically the kind of the basis that I use for coming up with some of the questions. So something that's related to being able to meeting deadlines, I guess, is the idea of being able to schedule a system in a way that is actually more or less provable, or, well, at least it's likely that the system, as it's scheduled, is able to meet the deadlines, right?
Well, there are many ways to schedule. There are two primary taxonomies, I guess. One are fairness doctrines, where everybody gets a chance to play, and one are priority schemas, where we're trying to ensure that important things happen in a timely way. And systems are often built with either, or often built with both features kind of in place. Some aspects of fairness and some aspects of real-timeness. The most common way to schedule, well, I guess it depends on the domain. The most common way to schedule avionics is with the cyclic executive. Even though it's demonstrably suboptimal in terms of performance, it's very, very simple, so it's very predictable. But in other environments, the most common way to schedule for hard real-time systems is to use priority-based preemption. And within that, the most common approach is RMA, rate monotonic analysis, rate monotonic scheduling. And in that, if you make the assumption that the deadline occurs at the end of the period, and you have periodic event arrivals, then you schedule them such that the shorter the time frame between the period, the higher the priority. And it's an optimal schema, and it's also stable. By optimal, we mean that if that task set can be scheduled by any means, it can also be scheduled by RMS. And it's stable in the sense that in an overload situation, whereas when you can't meet your deadlines, you can predict ahead of time which tasks will fail. They will be the low priority tasks.
Yeah. So it's up to the application developer to make the non-important things, the tasks with obviously with not so high priority.
Right. In my book, Real-Time Design Patterns, I devote a chapter or two to the aspects of concurrency and selection of scheduling patterns, also sharing resources across concurrency unit patterns and that sort of thing. There's a lot of literature out there on different ways to do this. But ultimately, yes, the developer needs to select a pattern design solution that best meets the semantic needs of the application.
Yeah. If you do a cyclic scheduling, then you obviously have to know, first of all, the longest execution time of each of the tasks you run in that cycle, and also you need to know the typical or average or worst case load, I guess. So predicting the load that the system will have to deal with is probably a very important aspect of building a real-world, real-time system.
Well, that's why cyclic executives aren't very efficient, because if I've got to say a set of 10 tasks, and an event comes in that needs to be consumed by the 10th task, and I'm on task 1, it has to wait until that 10th task gets around to executing before it can handle that event. And in many systems, that's too late, in which case you might want to go to a priority-based preemption schema. There's a very famous case of the Busy One submarine simulator, which they originally did in Ada, and it would run for a few minutes and then it would just crash and just hang. And so they tried changing it all to assembly code, and that didn't work. So they brought in some guys from the SEI, and they analyzed it, and they said, well, what you need to do is, rather than cyclic executive, use party-based schema and use RMS scheduling, and then it just ran as soon as they did that.
Cool.
And the original Ada ran. It wasn't the execution time of the assembly code that was the issue. It was really the ordering and the priorities of the events coming in.
So we talked already about task priorities. There's other terms that I've read, and actually I don't really know how they exactly relate. These are urgency and importance. Can you explain?
Okay, that's very important. Within priority schemas, there are two primary scheduling sub-schemas, if you will: urgency and importance. Urgency, if you think about the utility function, okay, urgency is the length of time before the deadline occurs. So it's a measure of the nearness of the deadline. So something that's near in time is urgent. Something that's far in time is not urgent. In terms of the importance is the height of that utility function.
Sure.
Something that's different importance is a higher function. It might be a value 10, rather than something less important might be a value 1. You can either schedule based on urgency, or you can schedule based on criticality.
So what you're saying is, if something is not very important but urgent, and something else is very important but not yet so urgent, you might still decide to do the important thing first.
Right, for example, suppose you're flying a jet plane, and you have to flutter your control surfaces every 50 milliseconds, or the plane becomes unstable and bad things happen. Okay, that has a certain urgency and, of course, obviously very high importance. On the other hand, suppose you're watching the movie Lost in Translation on the DVD player in the cockpit of your jet fighter. Okay, that has a frame update rate that has to occur every 10 milliseconds. That is more urgent than controlling the wing surfaces of the aircraft, but hardly, particularly with that movie, hardly as important.
Okay. See the point. So urgency and importance are two criteria that determine the priority. And actually, I think that's what you said before.
Right. And RMS, for example, is a fundamentally urgency-based schema.
So predictability, I guess, we talked about is an important characteristic. You want to predict how many, whatever measurements you can do. You want to predict how long something's going to take. You probably also want to predict the resources you want to use for these tasks, because otherwise probably your system will have to acquire resources as it runs, and that makes it unpredictable with regards to time, right?
Oh, absolutely. And predictability can be very problematic. It depends on the flexibility of the system. The least flexible systems are the most predictable, right? Because they don't have to respond to so many changing demands. The most flexible ones are the most difficult. So for this reason, what many people do is they do what's called worst-case analysis. They say, in the worst case, I'll get events coming at this rate for this long, with this kind of a burst length, and I'll have to handle this many messages for so long. And there's a number of ways to model that worst case. It can be, for example, if things are aperiodic, for example, they occur when they occur. Somebody's typing on a keyboard. What you would do in terms of a worst-case analysis, you say, well, what's the fastest time this person can type on the keyboard? Well, okay, that's 40 milliseconds between key presses. This is like a monster, a typist. You can burst out certain words because you've got them kind of like memory coded. However, most of his typing will be much, much slower than that. It might be average 500 milliseconds. Right? But because you're doing worst-case analysis, you assume, if I assume that this is periodic, at the rate of 40 milliseconds, I'll know I'll meet my deadlines. So as a result of the worst-case analysis, what often happens is I over-design the system for cases which are rare, but the result is I get more reliable systems, because if that rare occurrence occurs, I can still handle it.
Sure, yeah. But that, of course, wastes resources if you have to handle many, sessions or many channels at the same time, and you plan for each with the worst case, then you obviously waste resources. But that's the price you pay, I guess.
Yes, ultimately it is. And sometimes if you can relax worst case assumptions, you can greatly decrease the price of the systems. I mean, the FAA had a system they were trying to replace the air traffic control system a few years back, and they wanted basically 7 nines of reliability, and they failed. They spent $3 billion and failed because they had over-specified the system that they couldn't meet.
Yeah. So another thing that comes to mind here is, of course, then also graceful degradation. I mean, at some point the system needs to detect that the load is actually higher than it was designed for, and then do something that is not crashing, I guess.
Well, that's what we call the defensive design. You have expectations about the range and value of variables, of the arrival times of the events, and so on. And when you do defensive development as well as defensive testing, you test boundary conditions around that range, as well as some things that shouldn't in principle occur, just to make sure that, for whatever reason, if the assumptions are wrong or the environment changed, that you still don't do the wrong thing. Maybe the right thing is throwing the event away, maybe it's causing a reset, maybe it's resetting the system, maybe it's notifying the user, but making sure that the right thing happens at all the right time. This is crucial for high reliability systems, such as fire control systems, avionic control systems, stuff that I work with all the time.
And that's also that leads into the topic of fault tolerance and fault mitigation, and that's something we're going to talk about actually soon with Bob Hanmer, who's writing another book on this topic. So this goes together quite well. So let's look at the maybe main architectural styles for building real-time systems. You already touched on these things, event-based versus time-triggered. Can you maybe give a small, concise definition of what the difference is between these two systems and where they are used?
Well, let me give you a definition of architecture first. The harmony process, which is the process that I developed and is the process used in consulting from Teleological. In the harmony process, there are 5 really fundamental views of architecture, and there may be a few other ones depending upon particular circumstances. But the 5 fundamental ones are the subsystem component architecture, which are the large-scale pieces of the system, the subsystems or components, whatever you want to call them, their interfaces and their responsibilities. The second is the distribution architecture, which is how these elements are distributed across multiple address spaces, how they find each other, how they communicate reliably, and how they collaborate. Next, we have the concurrency and resource management architecture, which is the identification of the task threads, the concurrency units, how they're scheduled, how they share resources, and how their event properties are characterized. Next, we have the safety and reliability architecture, which is how we identify, isolate, and correct faults at runtime, usually through the means of design patterns and redundancy at the architectural level. And lastly, we have the distribution architecture, the deployment architecture, which is how the different engineering disciplines, such as software, electronics, mechanical, chemical, optical, whatever, work together in the system, what the interfaces are, what the responsibilities are, and so on. So we view in the harmony process architecture as one or more design decisions, design patterns in each one of these different architectural areas. Okay. So what was your question again?
The question was reactive or event-based system versus time-triggered systems. Probably wrong to call these architectures, but they are, the way the systems execute is probably quite different.
Time-triggered systems are usually considered to be primarily periodically based, right? So that is the event arrival pattern for the event is periodic, and there's some variation on the period called jitter. And based on that, you can assign your priorities using means such as earliest deadline first, rate monotonic scheduling, or whatever, to achieve the schedulability and predictability of the outcome. The event-driven, or what we call aperiodic, or permanently aperiodic events. And these events occur when they occur, when the user decides to do something, when an event in the universe of interest happens. And so these systems are actually lots of times modeled as periodic with the worst case, the minimum inter-arrival time of those events modeled as a period.
Mm-hmm.
And that way, even though you may over-design the system, you're robust against conditions that may rarely occur. Another way to actually model aperiodic systems is to look at, even if they can come infinitely fast, they don't come for infinitely long. Any system where the events come infinitely fast or infinitely long, you can't meet those deadlines. Okay?
Mm-hmm. Mm-hmm.
Cannot be done. So you have to somehow bound it. And so another way to bound the problem is you might have a burst length, which is a known fixed length. It might come infinitely fast, but they might only be a burst of 100,
mm-hmm.
right? And so you have some limit to that, and then there's some rest interval between that burst. And then you can analyze using stochastic means like Markov chains, queuing theory, and so on, to analyze the system for scalability and predictability.
So is that something that's done typically in practice, that you really analyze and simulate a system, or is it more like, oh, let's build something and then let's try whether it works? Or what's the best practice, or does this depend on the safety issues there?
Best practice is to do the analysis. However, I think it's rare. The most common engineering approach is prayer. That they say, "Oh God, I hope this works," rather than do the analysis. And I think that's unfortunate because there are tools out there. Cryopacific, for example, has a tool called RapidRMA that can do some stochastic as well as RMA kind of analysis. Mm-hmm. So there are tools out there that can help you analyze the tools. And there's a standard called the UML profile for scalability, performance, and time, mm-hmm. which identifies a set of peg values, metadata, mm-hmm. like priority, worst case execution time, blocking time, and so on, that you can use to tag your elements with, and in UML. Mm-hmm. Speaking, and then these tools can read UML because there's now this defined standard. Yep. Can read it, for example, with the XMI, analyze the model, and then say whether or not you can always meet your deadlines, or what you might have to do to ensure that you can always meet your deadlines.
Yep. I mean, probably it's the same problem everywhere, that if you want to do simulation analysis, then your models have to be formal, correct, and complete, and that's probably not many people actually want to do this, so they probably just hack together something and then try.
Well, that leads into another set of issues. I'm a big believer in using UML in an executable way, mm-hmm. all the way through development. It's very kind of an agile approach. The point at which we're doing continual execution. So if I'm working on a system, for example, I'm helping to architect a helicopter design in Canada right now. When I architect a system, work on a system, I build it as a piece of incrementally executable models. Mm-hmm, mm-hmm. So even at the outset, I have something, day one, I have something that runs. Yep. And it has a very specific purpose. Yep. And this model then evolves over time, and it always runs. Yep. So daily, I'm running the system, it's 10 times, 20 times a day. Yep. So I can always do that kind of execution. But you're right, in terms of doing some analysis, we have, if you look in, there's a book by, I can't think of the name right now, there's Practitioner's Guide to Scalability Analysis, mm-hmm.
by
Kluwer Press. Mm-hmm. And it's kind of the Bible for rate monotonic analysis. Yeah. They give a number of different ways, a number of different techniques to analyze systems, whether they have stochastic properties, whether they are event-driven or time-driven. So there's a number of different ways you can analyze the data. And you can do this what's called global RMA analysis, where you just identify your task threads and some of the resources, what the blocking times are, mm-hmm. at a very high level, do some quick analysis. But then over time, if you evolve these models, you can add more and more fidelity and detail, mm-hmm. and get better answers. I think the time to find out that you missed your deadlines is not when the plane is in flight. Okay, the time to find this out is before the plane is even on the tarmac. And to do that, you have to do early executions. So in the Harmony process, what we do is based on the use case analysis, what the functionality is, and applying the quality of service, we determine the overall performance budgets. So I have to do my control surface, fluttering within 50 milliseconds so the plane is unstable, okay? Mm-hmm. Then I identify inside the aircraft the chain of elements that have to work together to do that, and each one of them gets a piece of that performance budget. Mm-hmm. And it's unit tested against that part of its performance budget, mm-hmm. Mm-hmm. such that when it comes back, if it meets the performance budget, I know the entire chain will work. And the earlier you do this, the better off you are. It's kind of like when you argue with your wife, okay? If you wait 6 weeks to resolve an argument, it's a huge deal. We're talking lawyers, right? Yeah. It's a major, major deal. If you resolve it that evening, it's quick and easy.
Yep.
It's less pain. The longer you wait, the more pain it is. So you really want to make these decisions, particularly in an environment where you expect performance to be a concern, early as you can, and track it and monitor it all the way through development. And it's part of the harmony process.
And well, now that we were talking about that, talking about the modeling and description of real-time systems, you already mentioned the role of UML. So I guess these days there aren't any other formalisms that are used for that kind of stuff. I remember Room, R-O-O-M.
Well, Room is an offshoot that kind of died on its own. There were these weird notion of these capsules, and there are things like structured classes,
right,
and they're equivalent, but really SDL concept of blocks preceded Room, and you could argue the etymology is much more towards SDL than it would be towards Room.
So is SDL used much these days, or is it all more or less subsumed under UML 2.0 or 2.1?
SDL, in my experience, there's certainly, particularly in telecom, and particularly in Europe, there is still interest in SDL, but it has been largely replaced by UML and SysML. And that's my experience.
So which diagrams of the UML, or which UML subset is particularly useful for these kinds of systems?
Well, I think you can build any system with 3 diagrams types.
Okay.
The other ones do add value, and I'm not saying you shouldn't use them, but there's 3 core essential diagrams you need. You need to have a structural view, and that's provided by class diagrams of various kinds. And UML, unfortunately, defines class diagrams, package diagrams, structured class diagrams as if they were different. They're not different. They're the same diagram.
Absolutely.
Okay? It just depends on what your emphasis of the purpose of the diagram might be. So class diagrams show the structural elements and the relations. So that's an important key view. For example, that's how you do concurrency analysis. Identify these active objects. They are the units of concurrency, and they contain the semantic objects from your analysis model or platform independent model as parts, and they choose the context of that thread. So that's how you do your concurrency modeling, for example, in UML.
Okay.
The second diagram you need are the state machines, because most of these systems are heavily state-driven, and state machines are a crucial way to represent the behavior of such systems as they receive events, change states, and perform actions. And lastly, sequence diagrams are crucial, both in terms of requirement specification of the system, understanding what you expect the interaction to be, as well as execution of the system. So if using tools like Rhapsody, when you run the system, you can dynamically create sequence diagrams of these corresponding elements as they collaborate. And then you can compare it either manually or automatically with what you expected. You can say, that's what I expected, or wonder why it's doing that. That's not what I expected at all. So with those 3 diagrams, I can build any system.
So, but I always thought, and probably still think, that sequence diagrams are not that useful because you cannot describe closed behavior, because they always design or describe scenarios. But if you use it in the way you just explained, by describing expected scenarios and then recording the actual behavior and comparing them, then I guess this makes quite a lot of sense. I didn't think about that.
Well, if you have a set of collaborating classes, this also works at the use case level as well. But if you have a set of collaborating classes, many of which have state machines, you can think of the sequence diagram as a specific set of paths through those set of state machines.
Scenario,
Right? That's a scenario. And then, as what I really want to have to describe the overall behavior is every transition in all the state machines in my collaboration is represented in at least one sequence diagram. And then I have what Harmony calls the minimal spanning set. That is, all the transitions and all the state machines are handled at least once in sequence diagrams. That gives me coverage over the behavior of that collaboration.
So it's fair to say that you use sequence diagrams to describe test scenarios or test cases, and then do coverage analysis and compare it with the running system.
Yeah, but state machines are also crucial. I mean, the fact that they have to be, if you will, different views. Another reason why to have sequence diagrams, I do a lot of stuff with the Defense Department here in the U.S., with regulatory agencies and government agencies in Europe and different places, and there is no way that you can teach your typical customer to read a state machine. It's just not going to happen. But in 5 minutes, I can show them how to read a sequence diagram so they can evaluate the proposed behavior of the system to see if that's what, in fact, what they want.
Yes. Good, very good point. So the stuff we talked about, especially this last one, the ability to illustrate a system's behavior to, let's say, well, outsiders or non-techies, that's using modeling for documentation. You already mentioned that you use models to simulate a system and to analyze properties of the system. How important is code generation for these kinds of things? Do you actually generate the complete system from these models, or is code generation still more or less a niche these days?
Well, I think using UML or modeling in general for documentation gives you a very marginal value for the effort attained. I firmly, strongly, fundamentally believe that the model needs to execute, it needs to be semantically complete. Yeah. And if it is semantically complete, you can generate the code.
Yeah.
My experience, I've consulted to something like 350 customers, okay, different companies, over the last 11 or 12 years. And over those, most of them, almost all of them, in fact, generate 80% or more of the code from the model. Okay? So, yeah, they do generate the code, they deploy the code, they use that code in the developed systems. Okay. Only a few of them. Now, in a typical system, there might be, a device driver that you've already written, it still works. There might be a math library that you want to use from somebody else. So there's a small amount of code you don't generate.
That there's always a platform against which you build your system. I mean, you always reuse libraries and stuff. You wouldn't regenerate them anyway. So I think that's trivial. That's all. Right,
but well in excess of 80% of the code in a typical system that I consult on is generated. Cool. This is true in helicopter designs. This is true in medical systems. This is true in telecom systems. This is widely true. And I think going to code-based systems is really like going back to assembly language from C.
Sure. Yeah.
It can be done, but the bottom line is we use modeling because we can do more in less time with fewer defects.
Yeah. Actually, I mean, I agree completely. I mean, I'm working also in this model-driven world, not so much in real-time systems, but in other kinds of systems. And well, it's exactly my point. Why would we write these things manually? But many customers are still skeptical, especially if it's mission-critical stuff. They say, well, yeah, but we don't really trust the generator. So probably the consequence is to improve the generator as opposed to writing things manually.
Well, what I recommend for those people, and I've only seen my fair share of those people, is that they should look at the code.
Yeah.
I mean, so what we've done sometimes, we've gone and say, well, we'll go ahead. If you want to assume you want to write code, that's fine. In the meantime, there's still value in just executing the models. You know that your design is right. Yeah. Okay? Before you worry about the developing the code for the implementation. But as you develop the code and you review the models, review the code too and see what you think. Yeah. And so far, to a company, everyone has said, yeah, that's about what I would write. Or sometimes it's better than what I would write. Yeah, exactly. So it does depend a lot on the quality of the cogeneration, but the state of the model compilers today is that many of them are really pretty good. Mm-hmm. Of course, my experience primarily with Rhapsody, but but there are tools out there that can generate deployable quality code in real-time and embedded safety-critical applications.
Mm-hmm. So if I want to model the complete application, then I also have to model all kinds of quality of service aspects. You already mentioned this UML profile, what is it, schedulability and so on, you mentioned it before. So is that the best practice way of how to specify timing, resource consumption, and other quality of service aspects?
Right. Basically, you model them as constraints and as stereotype elements. So you might take, for example, an operation, and you add the stereotype real-time action. And along with that stereotype, you get tags, values, which are placeholders for the metadata. Yep. Like, well, what is the worst-case execution? What is the average execution time? What is the blocking time? And so on. So that you can do formal analysis on that model if you want to.
Do you also do... go ahead.
Well, so that's the way you typically represent them. Typically, a result of a stereotype, you get tags, which are then explained or expressed in UML constraints to tag these elements with specific metadata around their quality of service, around their performance.
Mm-hmm. So UML constraints typically just basically check that a system conforms to certain properties. Do you also use constraint solving as a kind of forward optimizing a system towards given properties?
Most constraints are not really imperative. That is, if I have an operation and I give it a constraint of 20 milliseconds, I'm not going to generate different code if I change that constraint to 15 milliseconds. Right? Mm-hmm. What changes is whether or not that code on the target platform with the target environment is right or not. So what most of the constraints are actually going to be result in testing conditions rather than imperative cogeneration.
Yeah, or watchdogs that stop something if a time limit is overrun or something.
Right, so make sure there's timeouts on the state machine for the systems need to detect certain timeouts occur. But most of them are testable kinds of things rather than code degenerative things.
Okay. So you mentioned already the fact that embedded and real-time systems in particular aren't software only. You mentioned the chemical engineers and the optics and the mechanics and the electronics and stuff.
Right.
How much? You also mentioned SysML. So do these people use SysML these days? How important is SysML already in practice? We're going to do a separate episode with I don't know what the name is, the spec lead of the SysML team. He already agreed. But so what's your experience with SysML? Is it already a factor these days?
Well, SysML is still it's an adopted standard but not a release standard.
Okay.
So first of all, let's say it's not actually officially released. It's adoptive, but now it's going through what's called a finalization process where you're trying to fix defects. Nevertheless, even though it's not a released standard, it's just an adopted standard, I see it daily. We see, all kinds of companies, I won't mention any names, but all kinds of aerospace, transportation, medical manufacturers, telecom manufacturers using SysML in their daily work. Now, normally what's done is they use SysML, and really, to be honest, SysML is just UML.
Sure,
okay?
With a couple of profiles.
SysML is just UML. There's really nothing of consequence added. Now, that will make some people upset, okay? But the major reason SysML became acceptable to system engineers was because we named the word class to the word block. That's what made it acceptable, okay? Because it didn't sound like software stuff. Well, there were a couple of other. There were a few things added, like parametric diagrams, or just really a usage of a kind of a class diagram. They added. There were, I think, important additions to activity diagrams, making them continuous in time as well as continuous in behavior. And that, I think, is an important step that should be folded back into the UML. But other than that, there's really minor things. They added like an allocation dependency, and they added a requirements type. But these are really, remember, these are just stereotypes. UML, or SysML, is a profile of UML, which means that they can only, in very minor and well-controlled ways, extend the UML. And these are very, very minor extensions. Okay. So having said that, SysML is a standard now. It's widely used by system engineers. And, of course, the most common approach to system engineering is to use Word and bang out text or PowerPoint engineering, we call it. But nevertheless, those people that are trying to move up the abstraction chain to be a little more precise are adopting SysML in droves. I mean, every place I go, I see SysML.
Okay.
With their systems work.
Cool. So now that we talked about all this modeling stuff, let's get a bit more concrete. So what are the programming languages used these days for building real-time systems? Is it still, okay, I know that this question is probably stupid, but what about Ada?
I do see Ada occasionally, although it's used more in Europe than it is in the U.S.
It's interesting because it came from the U.S.
Yeah, it was mandated standard by the Department of Defense, but for a number of reasons. One was the compilers were so expensive. $25,000 for a compiler was just outrageous. When you could get a C++ compiler for $500, right? Yep. And so you had to get an exemption to do something else. And in fact, everyone was getting an exemption, so they removed the mandate. Nevertheless, you still see it in Europe, although I'd have to say it's waning. Its use is waning. The most common language for embedded real-time systems remains C. Yep. Followed in some environments relatively closely by C++. Real-time Java has not made a real impact. You see it in systems where the user interface is a primary concern, so people using like Swing and AWT libraries for that. So you do see it in some places like telematics, those automotive telematics, things like that. You do see it some, but really it's a minute market share compared to C and C++.
So you say C++, some people say that the plus is the problem because it becomes non-deterministic because of all these virtual function tables. Is that really a concern, or do you limit yourself in using C++ to make this a non-issue?
Well, just because using an index in the virtual function table does not mean it's not predictable. right? Because all that is indexed offset addressing. If you want to go to assembly language and look, it means that I'm going to use incremental add to the accumulator offset addressing to find the element, right? And that's a fixed time frame, so it doesn't add or detract from the predictability. It's like as if you took all these functions, you put an if statement. If this is true, we do this block, or this other block, right? So in terms of predictability, that's not an issue. The only place where it is an issue is in the DO-178B standard. Because it's a very kind of paper-heavy standard. It's very about kind of static desk checking analysis rather than testing, rather than a kind of more modern analysis. Because of that, it's fairly difficult to get things with virtual function tables approved. Most people abandon the virtual functions when they're going to use C++, or they use C particularly for level A and level B certification. Now, there is a new standard. There's a meeting coming up in September, I think, in Brussels, for the DO-178C standard, which is not supposed to be out for another year or change yet. But supposedly that standard is going to be much more object-friendly. I think where software engineering is in terms of the DO-178B standard is about 1982. And there have been some advances. And this is a very, very conservative community, which is not a bad thing, by the way, I want to point out. It's not a bad thing when I have to fly on the plane. But nevertheless, it's a very conservative community. And so they are slowly adopting, and hopefully we'll get them into the late 80s in this new standard C, that is, cognizant of object orientation and encapsulation. Encapsulation in DO-178B is kind of a bad thing, right? I mean, so all of the current best practices in terms of software engineering are not exactly prohibited by the DO-178B standard, but they're not exactly recommended either. And sometimes you have to work around them. So that's the only place where I see that's really an issue. And that's really only a regulatory issue. It's not really about performance or safety issue per se.
So how important is static code analysis? I thought Ada had the property of being more or less analyzable so that you could look at or analyze the code with tools and prove certain properties. I think it's probably more the case that this is done on model level these days, so it's not that important that the language actually supports that, right?
Well, as soon as you use access types in Ada, it's no better or no worse than C++.
Okay.
Right? I mean, as soon as you start using references to things and pointers to things, then you have the issues of indirect invocations. If you stay away from them, you can stay away from them in C too if you want. You can stay away from them in C++. You can also stay away from Ada. So it depends if you put things on the stack or you put them on the heap. And as soon as you use pointers, you're typically using things on the heap, right? And if anything, Java is a bit worse because everything goes on the heap in Java, right?
But not in real-time Java, right?
I'm sorry?
Not in real-time Java. I think there is ways to.
Well, it depends. There are two different real-time Javas.
Okay.
Right. One has a kind of a wart on the side of a normal virtual machine. That's the J consortium Java for the real-time stuff, and one has a completely different VM, which has stuff that's more deterministic. But nevertheless, I mean, no one's really using either to any great degree. But nevertheless, the issue of analyzable means that you just have to be able to trace the values of these function pointers. And the problem about doing static analysis is you don't know at the point that you're doing analysis what the values of these pointers are, because they can change, right? But if you set them up, you can use patterns where you, for example, you do create dynamic creation of the objects, but only at the startup, and you never delete anything, right? It's one of the ways that people build relatively simple real-time systems. That's statically analyzable, right? Because you know after initialization what the values of all the pointers are. It's no different than having a reference, an address that you call into the function. When they dynamically change, that's a little bit different. But again, most of these things are really statically defined. So the current state of tools may not be able to statically analyze it very well, but really, fundamentally, it should be statically analyzable.
So let's briefly look at the real-time operating systems. How are they different from general-purpose operating systems? I guess one thing is predictable scheduling.
Well, the scheduling can be different. That's certainly one aspect. They also tend to be more scalable because on Windows you can't really scale down so well. I mean, you get what you get. and don't get me started on Windows. But generally speaking, they have mechanisms in place to do not only rate monotonic scheduling, detectable scheduling, but also resource management, event processing, and so on. But they really are underneath just kind of minimalist operating systems. They don't have necessarily all the networking stuff you might find in a desktop operating system, although they do sometimes have that, or at least as an add-on component. But they tend to be a bit more
configurable,
robust, right? And far more configurable.
Okay, so let's briefly look at some of the best practices for building real-time systems. One thing that I've heard somewhere is that you always try to isolate the real-time part to a very small kernel and make all the non-time critical stuff more or less put that outside of the kernel. I guess that's a good idea to keep the complexity of the real-time issues as small as possible.
Actually, I haven't seen that. What I've seen, no, I really haven't seen it very much. What I've seen is safety critical aspects are isolated. But the real-time aspects are not. For example, I worked on an anesthesia system once where we had a bunch of stuff which we were doing distributed proportional control loops, doing some closed-loop control. And that part had to be real-time. That was done with the VxWorks kind of operating system, and that was done with the safety critical aspects. It was actually closed-loop control of delivery of therapy, anesthesia drugs. The other stuff, there's a bunch of stuff around assisting the doctors to make good decisions by adding all kinds of graphical views and so on, which was not feature critical because it was just an assist. So we put that stuff isolated away on an NT machine at this time to have it different. So the safety critical aspects I've certainly seen isolated away, but usually if someone decides to do real time, unless they're going to run multiple computers, depending on the size of the system, then they'll do it all real time. That's what I see much more commonly.
Okay. So you mentioned already the distribution challenge. What gets more difficult, and how do you handle if you have to build a distributed real-time system? So somehow the timing constraints have to be enforced over multiple machines and over networks and buses and all that stuff.
Well, there are two fundamental problems with distributing systems, right? One is that networks are inherently unreliable, as opposed to just running on a computer. Generally speaking, if you send a message to another thing on the same computer, it always gets there, right? You never lose it unless you're running Windows. But otherwise, you never lose it, right? As soon as you distribute, there's loss because of noise, dropouts, whatever. There's now loss, and it's orders of magnitude more often. So that's one of the primary aspects you really have to consider when you're distributing systems. The other thing is that, it's somewhere else. And so that takes time and effort, and you have to go through more software protocol stacks to actually send the message, or you do something like shared memory or something like that. You have to have some more elaborate means to collaborate. So instead of just invoking a function or referring off to data, say, here, munch on this, I have to send much more information because they're not in the same neighborhood, right? So they can't do the same shortcuts that I can do. And so somehow I have to communicate that. And the way we do this is over wires or over the air with communication protocols. And so now that opens up a whole can of worms, if you will, for an opportunity to make mistakes, to distribute things across. And then depending upon the nature of the communication channel and the protocol being used, it can be deterministic, it can be non-deterministic. For example, Ethernet. Ethernet saturates at about 30% load. And what that means is, because it's a collision detecting system, when you get a collision, you have to back off and you retry at random times. So at 30% load, you're spending all your time resolving collisions and really essentially none of your time actually getting data across. As opposed to something like a CAN bus, which is a priority-based schema based on the first 11 bits or 29 bits, depending on which version of CAN you're using, a bus, you have a priority scheme. So if somebody detects that, it's called a bit dominant scheme, where if you write a bit out, what's called subdominant bit, and you read what actually goes out on the bus, if it's not what you wrote, someone else is also trying to master the bus, and they win because they put out a dominant bit when you put out a subdominant. And so in that sense, it's much more predictable. So depending upon the traffic, that bus has to handle. And the nature of the timeliness of that traffic is so that you want to select one bus or network over another one.
Okay, so final topic. How do I test real-time systems? One thing that you probably have heard about is the Heisenberg bug, where trying to measure a bug or debug something actually influences what you want to measure. So this makes it quite complicated, I guess, to test and debug real-time systems.
Oh yeah, the Heisenbergs are always fun. Well, basically, the testing, first of all, you have to understand right off the bat, you can't test everything, right? So you have to come up with a subset of the functional paths. You can perhaps test all static paths, but as soon as you add in all data variants, it's just an essentially infinite set of data paths and control paths you have to execute, and you just can't do that. Yeah. So what we typically do is set up your tests into a set, and the Harmony process identifies a set of different kinds of tests that you do, such as functional tests, where you pick kind of values in the kind of middle for a particular functional path. You do static paths, make sure all your transitions in your state machines, you can do the code level or the model level, depending on the level of analysis you want to do. You also can do statistical testing, where you do random samplings across the distribution of your data sets. You can do boundary tests, where you test right around the boundaries, things that are invalid data, out of valid data. Stress testing, volume testing, where you throw data at a higher rate than you expect for longer than you expect to have it. Those sorts of tests. Now, the way you come up with those tests is you can either be kind of code-based, text-based approach, or you can be model-based. And I'm, again, a big believer is moving to the models as much as we can. So we have tools like Test Conductor and ATG. Test Conductor takes your sequence diagrams you identified for your use cases and uses them as test vectors. And this is what I think is really cool about the approach, because now you're capturing your requirements in an inherently testable way, rather than, say, writing a bunch of text describing it, and then the test guys figure out, well, what does that mean? And developers figure out, well, what does that mean? You capture them as formal model artifacts, sequence diagrams, and say, this is what I expect to happen. The developer knows how to build against that, and the tester says, that's what I need to test against. And test conductor tools that can apply those tests automatically. And then you have tools like ATG, Automatic Test Generator. What that does is it parses your model and makes sure that there is a test that covers every, for example, transition path in a state machine, branch point and activity diagram, all your operations and actions get validated, and that's sort of coverage testing, but at the model level. And so I give you some. So you get some assists in those. I gave a paper last year in D.C. at the testing conference there, and it was pretty well received. That's kind of what I had to say about that. So that's kind of how I believe. First of all, you have to identify the kinds of tests you want to test, whether they're stress, volume, performance, functional, stochastic, whatever, and then come up with test vectors. And UML actually has facilities that represent these.
And then those test executors also allow you to monitor timing, event numbers, distribution, deadlines, missed, and stuff, so you can actually test those timing problems.
Now, actually, there is an issue, because as you pointed out, Heisenberg had a point, right? As soon as you modify something to measure timing, you modified it, and so its timing is different. And so what I've actually argued for quite a number of years, that what we really need to do was instrument the ice heads so that it was completely non-invasive. But in practice, it's difficult, because all the different ice vendors have entirely different ways of representing their data. So in practice, it hasn't happened. But timing, you typically use in-circuit emulators, you use logic analyzers, ROM
really
emulators.
Down low.
Yeah, and so you use the symbol tables generated from your compiler to identify, I want to start and measure the time from here to here, or use markers, and then you use your oscilloscope to measure the time between those, something like that. That's what I've done. And it's a pain.
Yeah, that's
it
how
really
it sounds.
But I have to say, this really is the hard part of testing, is the performance testing. If you go to a black box, it's not so bad. But then if you fail the black box test, then identifying at which point it failed, it takes some investigation. This is why I try to obviate the testing as much as I can. And so I talked earlier about the performance parameters I give off to the unit level test, the functions, the methods, the actions, and so on, that propagated down the overall performance budget. So that when I test it in isolation, I'm relatively assured that when I put them all together, they've all met their performance, your propagated performance budgets, that overall the performance budget is met.
Yeah.
Now, early on, one more thing I want to say about that. Early on, when you do testing, you may not have the actual target hardware.
Yeah,
so then what I do is I take some measure, and in fact I might run some section of code, or 4 or 5 different sections of code on the actual target and on my desktop to get a performance ratio between the two platforms. And then use that. So if I expect 20 milliseconds on the target and my system is running 3 times faster than my target, then I know I can, if I'm doing it within 7 or 8 milliseconds, I'm on target for the actual target, right? And so there's that kind of testing can you do even really, really early to get some warm and fuzzy feeling that you're on the right track. What you do not want to do, in my experience, is waiting to the end and say, "Oh God, I hope this works."
Yeah, the later you test, the bigger is the black box you have to kind of trust, and
Right, and the more difficult it is. Yeah. So earlier, even if it's imprecise, the earlier is better.
Yeah. Okay, so what are you working on today? What is your professional hobby these days? What fascinates you? What are you playing with?
Well, I'm the last book I wrote, which was the RealTime UML workshop, has been out now for a few months, and that's doing very well. And there's been a buzz of interest about that. I run a website on Yahoo, RealTime UML, that has some discussions of related topics. I'm doing an awful lot of consulting. As I mentioned, I'm doing this helicopter work in Canada. But I'm in Europe. I'm consulting to places in Turkey, for example. I'm consulting to Korea, doing a bunch of different designs. And that's really taken a lot of my time. One of the interesting things that I'm doing, with the Harmony process, I'm actually capturing this now in a process authoring tool called EPF, the Eclipse Process Framework. And so that'll be released in a little over a month, at least in beta form. And so that's actually very cool, because now we can generate basically a website for process information, which we typically go in and we do a thing called an RDP, rapid deployment. And I'll come in, or one of my staff will come in, and we take kind of the base material, we create a custom process depending on the project, their business model, the business culture, the people involved. We kind of customize it for them. And previously, this has been captured in Word document, like a handbook, a guideline. It was a set of guidelines for how they should do their work. And now we're actually going to be able to customize this entire website for them, and they'll host it on their platform. And that's really, really cool. There's a lot of interest in that. So I spend a lot of my time and effort doing that. Another thing that's going on is the UPDM, the UML profile for DODAF and MODAF. That was just adopted last week, voted to adopt in the OMG. Which is not, by the way, oh my God, it's the Object Management Group. They own the UML standard.
Yeah, I think people know that, but I didn't hear that abbreviation.
You have to be careful with these acronyms, but it was voted to adopt, so there's still some work needs to be done on it. But it was voted to adopt last week in Brussels. That was good news. So I was working with that. I wrote the DODAF profile for Rhapsody. And that's doing well, but now we need to rev it to be consistent and compliant with DODAF 1.5, which was released in April this year, as well as the UPDM.
DODAF is what?
DODAF, the Department of Defense Architecture Framework.
Okay.
And there's a British version of it called MODAF, Ministry of Defense Architecture Framework. And there's a bunch of kind of related standards on this. There's one called NAF, the NATO Architecture Framework. There's a bunch of kind of related standards to that. So I'm doing a lot of work with respect to that, and also now incorporating kind of the SOA technologies into enterprise architectures.
Yeah. Okay, is there anything I forgot to ask you, something you want to say before we wrap this up?
No, I'm just excited to be a part of the industry. It's a very cool time.
You sound very excited and very involved, so that's cool.
Well, I never get up in the morning and say, oh, God, I wish I had something to do. I always have lots and lots to do. And one of the really cool things about my job, my life, is that I get to travel to all kinds of people doing all kinds of things, from secure radios to CAT scanners to embedded micro devices to cell phones to GPS systems, and find out what they're doing and how they're being effective, and kind of learn from that and assist in developing all these systems. It's really cool stuff.
Okay, Bruce, then I thank you very much for being on the show. I thought it was very, very interesting. I hope our listeners agree to that, and thank you very much for being on the show.
You're welcome, and thanks for having me.
Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.